All right, radicals are a really important tool we need to know for our synthetic toolbox, but let's do a little bit of introduction at first. And let's talk about heterolytic cleavage before we talk about radicals. What does the prefix hetero mean? Different. So if we think about a bond between two atoms, X and Y, all heterolytic cleavage means is that we're going to move two electrons onto one atom. They don't go in the they don't split evenly across both atoms. So when we do this, the atom X will become an anion, and the atom Y will become a cation. It involves a movement of an electron pair, and we always form anions.
This is chapter 11, right?
This is chapter 11. This is different than homolytic cleavage. What do you think might happen in homolytic cleavage? Yeah, they each get an electron. So in this case, we're not moving a pair of electrons. We're going to move each electron individually. So in this case, I'll show it using slightly different terminology. And to indicate that each atom received one electron, we show them as a dot. So we have X dot plus Y dot. And these are our radicals. And radicals always involve the movement of individual electrons. What do you notice about the arrows that I used? Yeah, the red arrows specifically. Let's narrow it down. Yeah, I didn't do double barbed arrows for the bottom one. So that's one way we try to distinguish the movement of single versus double pairs of electrons is we use different arrows. Specifically, the double-headed arrow means 2 electrons, and a single-headed arrow means 1 electron, and they are not equivalent to one another. They're very, very different. So this is 2 electrons, this is 1 electron. Make sure when you're drawing these that you very, very clearly indicate double-headed arrows versus single-headed arrows, or else you'll get marked down on that. I need to see that single-headed arrow whenever you're doing radical reactions. So let's take a look at an example of homolytic cleavage. In the example I have, I'm going to use R groups, all attached to a carbon, and I'm going to have a halogen over here. Halogen carbon bonds tend to be a little bit weaker, with the exception of fluorine carbon bonds. And so if we show this as a homolytic cleavage, this halogen will get 1 electron, and this carbon will get 1 electron. And now we end up with a carbon that changes hybridization. So we've got this p orbital, and this p orbital has 1 electron in it. Looks pretty similar to a carbocation, but instead of it being an empty p orbital, we have a solitary electron in there. What's the shape of this intermediate? Yeah, it's trigonal planar. Or sp2 hybridized. And then we also end up with that halogen as a radical. So the nice thing with radicals is that they follow the same stability trends as with carbocations. So what's going to be the most stable for a radical? A tertiary carbon or a primary carbon? Tertiary. So we do have to look at the stability trends, and let's make a note of that. It follows the same stability trends as carbocations. Pretty easy to remember. One thing that is a little bit different, yep.
Oh, so the dot on the X is an electron, right?
Yeah, and that electron can be localized on either side of the p orbital. Electrons are really weird because they don't behave quite like a particle. They can be on essentially both sides at any given moment. Have you guys talked about that in Gen Chem at all?
Yes.
Yeah, the improbability of knowing where an electron is going to be at any given moment. We just know it's going to be somewhere in that dumbbell-shaped cloud.
You know, you're talking about stability, but I was under the impression that radicals were crazy stable usually.
Radicals are normally very, very reactive, but we can still trap radicals, and there are a handful of radicals where we can actually isolate a compound in a bottle that is a stable organic radical at room temperature. They're not common, but next week's lab we're going to use one.
What happens?
It won't do anything. Yeah. So let's talk a little bit about resonance structures with radicals. And there's one really common resonance structure. I'm going to draw in all the hydrogens off of this. I'm going to call these ones our green protons, and I'll do this one as blue. These green protons are called allylic protons. This blue proton is called vinylic. But they're all very, very important. So let's take a look at what happens during homolytic cleavage with an allylic proton. So I'm going to just arbitrarily pick one.
Professor?
Yep.
Are the other two hydrogens also vinylic protons?
Yeah, vinylic protons are ones coming off of alkenes. Allylic protons are one carbon adjacent to the alkene, so they're right next door.
So those two are also...
Yeah. So let's take a look at the homolytic cleavage of an allylic proton. And I'm going to draw in all of our hydrogens so we don't get confused here. Actually, I'll try to keep the same colors even. So now we have a radical down here. And if we think about this radical, we said that this carbon right here has a specific hybridization. What was that? sp2. So we've got an sp2 carbon next to another sp2 carbon with a pi bond. We can do resonance with this, right? So what we can do is have this single electron get dumped down into that carbon-carbon bond, but we can't have a single electron form a sigma bond. It needs a partner, right? So where could we pull a partner from? From the double bond. So steal an electron from over here. Now we would get a double bond between those two carbons. And we have one electron left over that has to have somewhere to go. So it will hop over to that adjacent carbon. And we have an electron here. We have our same hydrogens here and here. So it's very similar to resonance structures with anions, but in this case we're moving single electrons, so we have to use the single arrows. And the byproduct or side thing was this allylic radical that popped off. So make sure when you're doing resonance structures you keep track of the arrows. It's very tempting to use double-headed arrows. Yep. No, in this case, if you try to determine the formal charge, it's still neutral. That's one of the weird oddities, right? So let's take a look at it just to practice. So this one highlighted in yellow right there that I've labeled sp2. Carbon normally wants how many electrons? 4. So we count half of the bonding electrons, so that's 1, 2, 3, and then the fourth one's the radical. So it has the proper number of electrons to be neutral. You occasionally run into radical species where there's also an anion or cationic charge in there, though. Yep.
So if the net charge is 0, what makes them so unstable? Because it seems like it's resonance stabilized and it's neutral, so that seems stable.
So these are more stable than a traditional alkane radical, but electrons really want to be paired, right? So just like with carbocations, it's all a spectrum of stability. Carbocations in and of themselves aren't that stable. They tend to react with other things like a nucleophile. Same thing's true with radicals. You can have differing stabilities in terms of a trend, but they're still somewhat unstable. They prefer to react with something else and get that electron paired. So there are two important things that stabilize radicals. Yeah. The first one was substitution. Just like we talked about with carbocations, tertiary is better than secondary, and that's better than primary. The fancy word for this was hyperconjugation. So if you've got sp3 lobes right next door to that radical, they can help stabilize it. And then the second one we just mentioned was resonance. So just like with carbocations, except now we're dealing with single electrons. All right, I'm going to give you guys a resonance, or a starting material, and I want you guys to draw all the resonance structures that correspond to it, and then we'll try to label them as major and minor.
How many more resonance structures?
There will be 2 additional ones.
How can we know when we should use a radical?
So if there is a radical to begin with, you're going to have a radical in all of your resonance structures.
I mean, well, you give us a starting material, but it has a double bond there. I mean, we can move it as just a normal double bond, and we can also treat it as a radical. But how do we know when we should treat it as a
Always try to start by moving your radical first. So try to move that single electron to stabilize it or delocalize it, right? Just like with an anion or cation, we want to move it around to as many atoms as possible. So try to find ways to delocalize that single electron. I'll give you guys a hint too. Can we move any electrons over to that carbon? No. It's already got an sp3 hybridization. We'd violate the octet rule. We're not going to move it over to the left. We've got to move it to the right. So I'll give us that one arrow down there. We can't have a half of a bonding pair. So what can we do to get that double bond moved up to that top right-hand carbon-carbon bond?
We could split that double bond over.
Yeah, move one electron from the pi bond over. Okay, so we're on our way. We've got a second electron in that pi bond, though, so we've got to dump that over here. Now we've got our double bond here. We haven't done anything with this double bond, and we've got a radical coming off of that carbon. Are there any other resonance structures? Yeah. So we can move this radical down here. We can move that radical over. And then that one over here. So we've got 3 different resonance structures. We've got to assess stability of these, though, too, right?
Are you even allowed to have a primary radical like that?
Yeah, you can, but let's label these as major and minor, just like we did with normal resonance structures. Which one's going to be major, the left, the middle, or the right? Ah, the middle. Why? Yeah, it's all of them have resonance, but the middle one has the radical on the tertiary carbon, so that's going to be our major contributor. This one will be our minor. And then this one will be our very minor. Radicals really don't prefer to be on primary carbons. Does that make sense? It takes a little bit of practice switching your arrow pushing, but just treat them as single electrons and remember the barbed hooks, not the double-headed. Let's take a look at radical reaction types. There are three main classifications of radical reactions. The first one has to deal with cleavage and coupling. Oops. So with cleavage, we've got this X and Y, and we're going to do a homolytic cleavage, so each of them gets a single bond, and we get two radicals out of this. What do you think coupling is? What's that noise? Is it the fan? All right, it stopped. All right, so cleavage, we break apart an XY bond into two radicals. Coupling is probably what? Yeah, putting it back together. So coupling, we just take X and Y and we put them back together. But they both have to be radicals in order for this to occur, and we can show this by using our single-headed arrows, and we form a new XY bond. So pretty easy reactions to remember. Shoot. The next type has to do with reactions with neighboring pi bonds. So there's one that's in addition to a pi bond. And let's try to figure this one out. So let's say I have a radical X, and I've got some sort of alkene over here. And I want to form a bond between that radical X and the carbon in the alkene. Well, I can take one of these electrons, dump it down. Where will the other electron come from? The double bond. And are we done? Nope, we've got to account for that second electron in the pi bond, so it will go over here. Now if we look at this, we've formed a new sigma bond, but we've also formed a radical coming off of the end. So with this sort of reaction, we're not eliminating radicals or making radicals, we're essentially propagating the radical. The next one is elimination, which is this exact same reaction but in reverse. So if we have a halogen coming off of a carbon with a radical next door, this radical can dump down. The sigma bond can donate one electron over. Let me clean that up. And then this other half of the sigma bond will get dumped over onto that halogen. There we go. So now we've got our halogen radical and we've got our alkene back. So these are essential for propagation of radical reactions. Where's, oh, sorry, I didn't see you back there.
So how would the sigma bond break in this case? Because sigma bonds are like incredibly stable. I understand how the sigma bond would form in the addition, but in the elimination, wouldn't it be different?
It really depends on the type of reaction you're looking at. Some reactions really favor addition to pi bonds. Other reactions thermodynamically favor elimination to form an alkene. It really has to do with the stability of the radical in each case. So if this is a really stable radical that you're forming here, it could favor elimination. However, if this is a really, really unstable radical, it'll favor addition to a pi bond. It just depends on the thermodynamics. Yep?
I think you just answered my question. I was going to ask if the radical is happier on the carbon or the...
It depends on, I'm kind of breaking this down to the simplest case possible, but it depends on how stable the radicals are in each of these reactions. Yeah. All right, the last two reactions are similar to one another. First one's called the hydrogen abstraction. And in this case, you have a radical that essentially steals a hydrogen from a neighboring molecule. So it'll reach over here, the sigma bond will break, and then the other half of the sigma bond will go onto this R group. And now the halogen has a covalent bond to the hydrogen, and the R group becomes the radical. This is pretty common in organometallic chemistry. The next one is called a halogen abstraction, and it works along the same lines. However, it's kind of in reverse. So we've got our radical that will steal a halogen off of something else. So now we form a new carbon halogen bond, and we end up with a radical intermediate, or byproduct, I should say. One thing I will say with halogen abstraction is you only see it with bromine and chlorine. Really, you only ever see any radical chemistry with bromine and chlorine. One problem with iodine is it's just too unstable. It doesn't ever really occur. The opposite end is fluorine, which is too unstable because it's so reactive that it'll typically explode on you. So people avoid radical fluorination chemistry. I remember hearing about a fluorine chemist that went into a talk. He said, I'll give you 3 reasons not to do fluorine chemistry, and he held up his 3 remaining fingers. It's incredibly exothermic and uncontrollable, so people just don't even attempt radical fluorinations for the most part. In this case, bromine radicals are more common than chlorine, and we'll talk about that in a second. With bromine, you have much more control because the reaction's slower and more manageable. All right, so let's go talk about halogenation of alkanes, which is the meat of this chapter. And I'll show you guys one trick. Before starting, you need to identify which proton would result in the most stable radical if removed. So identify a proton if abstracted. And I'll show you guys what I mean by this by using an example. Let me slide this down actually. I'm going to choose a cyclohexane derivative. And we have to identify protons coming off of this cyclohexane. Well, we could have some protons coming off of here, here, and here, so let's classify them. I'm going to label these ones as red, this one as blue, and the 3 methyl protons as green. So the red ones are all equivalent, the blue one's unique, and the green ones are all equivalent. If we think about it, we could say, well, what happens if we move or abstract one of those red protons? We would get a radical that looks like this. And if we remove a blue radical proton, or I keep on saying proton, if we abstract a blue hydrogen radical, we would get one that looks more like this. And last but not least, if we abstract the green hydrogen radicals, we would get one that looks like this. Which one's the most stable? Blue. So if we look at this, we'd say this one's most stable. Why is it most stable? Yeah, it's more substituted. So this was the most stable possible product, which means that blue hydrogen is going to be the most reactive towards radical reactions. So now that we've got that going, we can start our radical reaction. And radical reactions are always broken down into 3 elementary steps. The first step involves formation of a radical, second step involves propagation of a radical, and third step involves termination of a radical. So let's start this with step 1, initiation. So initiation of radicals happens a couple of different ways. Whoop. Yeah. You can have initiation using heat and homolytically cleave a halogen bond with heat. What's another way we could cleave covalent bonds and form radicals? Give you a hint. Think of skin damage.
Sunlight.
UV specifically, right? There's some sunlight that's not harmful. It's in the red region. But once you get down into the UV region, it will homolytically cleave bonds not only in organic molecules, but in your DNA, which is why UV light's really bad for you and you should wear sunscreen. So you've got a couple of options. We can either show this using the heat symbol, which is that delta, or oftentimes you'll see this H for Planck's constant, and that is that mu for frequency. That's the symbol for UV light. Some people will write UV, but mostly in the Klein textbook you'll see it written this way. Yep, it's a Greek symbol. It's not a normal V. So in this case, we homolytically cleave our chlorine, and we'll form 2 new chlorine radicals. So this is our initiation. The second step is called propagation. So let's use the same starting material that I had you guys work on, where we had a CH3 coming off here and we had a hydrogen coming off here. Now we've got a radical chlorine floating around in solution. What do you think might happen to that hydrogen? It'll get abstracted, right? So this radical will reach 1 electron out, steal one of these sigma bonding electrons, and then that other sigma bond electron will get dumped onto that adjacent carbon. Now we form HCl, and we form that stable radical. And remember, too, that this is trigonal planar. At least at that carbon with the radical coming off of it.
So, question to you.
Yep.
When it's set up like this 3 substitution, when there's 2, can you do like hydration or?
No, you don't see hydride shifts with radicals. You only really see hydride shifts with carbocations. That's a good question, though. All right, so we've got this trigonal planar radical. It's called propagation because we haven't killed the radical. We still have a radical around in solution, so we're just propagating its existence. Third step is termination. And there's actually a few different ways. Oh, shoot, I'm forgetting one other step with propagation. Let's take a step back. Sorry, guys. I apologize. So in that initiation step, we only cleave some of the chlorine that was around in solution. We still have other chlorine that's covalently bound. So this radical can come grab an electron from the sigma bond in the chlorine, and then we can reform that chlorine radical. That's why it's propagated. So now we've got chlorine, CH3. So we regenerate our radical. And now we've got a new carbon halogen bond. Now we can go to our last step, which was termination. In a termination step, what do you think might happen?
Terminate.
Terminate what? Terminate the radical, right? So it's going to be a coupling reaction. And there's 3 options to terminate our radical. One option is to have a chlorine radical find another chlorine radical.
Can you move out a little bit?
Yeah, just 1 second. Cl, Cl. And it can couple these together. So that's one possibility. What do you think another possibility might be?
Find the radical carbocation.
I could find a radical intermediate somewhere along the reaction process. So let's draw another termination step. Can I scroll up?
Yeah.
Okay. In solution, we might still have a little bit of this radical still floating around along with our chlorine radical. So we could have these couple together. And we can make more of our desired product. So that's another option. What do you think a third option could be? So we've got ClCl formed. We've got our other 2 radicals formed. Yeah, we could have 2 rings fused together because we've got reactive electrons on there. It's not the most likely due to sterics, but it might be a minor product. Actually, let me clean this up a little bit. CH3 dot, and we can have these 2 form a new carbon-carbon bond. Not the most stable looking molecule, but it could exist.
I have a question.
Mm-hmm.
I don't know. Can you give us an example? How is this applied to real life? Like, to what can you apply this? Like,
So let's say we have an alkane and we need to get a leaving group to come off of an alkane. By doing this reaction, we've created a new alkane with a leaving group. Now we can do elimination chemistry off of it. Or if it were a primary carbon, we could do substitution chemistry. We've opened up the door for functionalizing an alkane so that we can do something useful with it. Another really, really big feature that we're eventually going to get to is polymer chemistry. So most polymers, or I should say, yeah, I would say most polymers are created through radical chemistry. And so if you look at things like polyethylene or PVC piping or trying to think of other ones, Teflon's another one, a lot of those are made through radical reactions.
Why doesn't all of the chlorine just go to product, right? Why do you have an excess of chlorine floating around that can do other stuff?
So when you hit your chlorine with UV light, 100% of it doesn't get homolytically cleaved into chlorine radicals. A small portion of it does. And that small portion from step 1 that got turned into radicals will continue on to the propagation step. And then you could create more chlorine either from more cleavage of your chlorine around in solution, or you can just reuse the chlorine radical that was regenerated during that propagation step. You really only need a tiny, tiny bit of chlorine to be radically initiated for the reaction to continue on. Yep.
In termination, is the carbocation final product or the Cl2 the major product?
Is what the final product?
In the last one, is the termination major in Cl2 or in the carbocation or with the chlorine?
In this case, you could show any of them and I would give you credit for it. The key is just remembering that you have to show that radical eventually stopping somehow. So really any of these would be acceptable. All right, another important thing to remember too is that if excess Cl2 is around, it can / will keep on adding. So oftentimes during radical chlorination in particular, you end up with more than one chlorine getting installed because you have excess chlorine around in solution. So you guys remember in lab we used dichloromethane, and we're going to use chloroform soon. All of that is made by treating methane with chlorine gas and radically initiating it so that we can swap out the hydrogens with halogens.
When you say keep adding, do you mean like before when you had like the red and green?
So let's take a look at an example of this. Let's say we've got methane. Oops. So CH4 plus Cl2, and I'm going to write excess Cl2 and UV light. This will give you CCl4 plus CHCl3 plus CHCl2 plus CH2Cl2 plus CH3Cl. So if you've got excess around, you'll end up with the statistical mixture of all four of these potential products.
So what about in the case where like all of the hydrogens are not equally favorable?
In that case, it'll sequentially go to the next most stable hydrogen. Does that make sense?
Yeah, but will you still have like a primary radical product?
You might end up with a very, very small amount. And it depends on whether or not it's chlorination or bromination. And that actually leads me into regiochemistry a little bit. So with regiochemistry, we always have to ask ourselves, what position are things getting added to? And let's say I've got this starting material where I've got CH3s coming off here, here, and here. Let's say I do Cl2 and UV light. The major product will have this chlorine coming off of that internal carbon. And if you run this experiment, this will be present in approximately 72%. The reason being that this hydrogen, if it's abstracted, forms the most stable radical, right? None of the other hydrogens form a tertiary radical. However, radical chlorination oftentimes is less than selective. So you might get a little bit where you've got the chlorine coming off of one of your primary carbons. And in this case, you end up with approximately 28% of this product. So radical chlorination isn't super selective. Radical fluorination is not only dangerous, but has no selectivity really. Bromination is the most synthetically useful one because we do have control over it. So if we do Br2 in UV light, oops. Let's just, for the sake of comparison, whoop, I always forget carbons off of here. Ah, shoot. Here we go. All right. With radical bromination, the product on the right, you get almost perfectly in 100%, and you get almost no bromine coming off of that less stable carbon. So synthetically, radical bromination is much, much more useful than radical chlorination. And you don't see radical iodinization. At least I've never seen it for a synthetic reaction. All right, one last thing before we leave is stereochemistry. So let's say I have this compound, and I've got CH3, and I treat this with bromine and UV light. We know that we've got a mixture of products based on our experimental data, and it's important to remember that this hydrogen in blue is going to form the most stable radical if it's abstracted. So we might end up with 50% with our new halogen pointing in the back. And we might end up with 50% with that halogen now pointed in the front. So you do have to watch out for a racemic mixture of enantiomers. Why do we get a racemic mixture? Yeah, so if you remember, that intermediate radical that we form is trigonal planar, and you can have attack from either face. So just like with carbocations, you have to worry about forming racemic mixtures when you're doing radical chemistry. All right, I think that's where we're going to stop today. Tomorrow when we come in, we're going to do halogenation, practice problems, and learn about that anti-Markovnikov reaction that we covered in Chapter 9.